So in this video we're looking at chemical equilibrium, and we're in particular going to focus on the Haber process and the contact process. So our learning intention is to use Le Chatelier's principle to explain the effect that temperature, concentration and pressure have on the Haber and contact process. So first we'll look at the Haber process, and the Haber process is basically the production of nitrogen, and it was put forward by a German chemist called Fritz Haber in 1908. And he discovered that reacting nitrogen and hydrogen, you would form a gas called ammonia. He also discovered that the reaction doesn't go completely from left to right, that there was also a reaction from right to left with the decomposition of ammonia forming nitrogen and hydrogen. So in the Haber process, the forward reaction, or the production of ammonia, is an exothermic reaction. So that means that delta H is negative, while the reverse reaction, the decomposition of ammonia into nitrogen and hydrogen, is endothermic, meaning that delta H is positive. So let's look at the effect, first of all, that temperature has on the Haber process. So temperature, if we were to add heat to this reaction, in order to counteract the heat, the reaction needs to cool down. And we know that the cooling reaction is the endothermic reaction. So that would mean that we would be producing more of the reactants. So basically, a high temperature will cause the reverse reaction, or the decomposition of ammonia into nitrogen and hydrogen, to occur. However, with the Haber process, we want a high yield of ammonia, so we want to produce lots of ammonia. So a high temperature, or increasing the temperature, is no good to us. To maximize the yield of ammonia, we need low temperatures, and in order to counteract this temperature decrease, the position of equilibrium shifts to the exothermic side, i.e. the forward reaction. As to counteract low temperatures, we need to heat up, so that produces more ammonia. Now, we know from rates of reaction that low temperatures would have a very slow rate of reaction. So in order to get a high yield of ammonia, we can't really use low temperatures. So a compromise temperature of 500 degrees is used. So next, if we look at the effect that concentration has on the equilibrium, we can see a reaction here in the top corner. If we increase the amount of nitrogen that is present, or if we increase the concentration of nitrogen, we will have more reactants present than products. So our stress has been applied now that there is now more reactants. So what we must do is we must work, the reaction must work to try and absorb these extra reactants that have been added. So, according to Le Chatelier's principle, to re-establish equilibrium, more nitrogen will need to get used up to form more ammonia. So that means that the forward reaction is favoured. Similarly, if I was to remove ammonia, what would happen is the equilibrium would shift to the right, because to re-establish the balance, the reactants would react more to produce our product. So if we decrease the concentration of our product, the reactants are going to work really hard to produce more of the product. So the forward reaction, again, there would be favoured. So the last stress that we're going to look at is pressure, and here's our reaction again. And we know that changing pressure only affects equilibrium if the reactants and the gases are products. Now, nitrogen is a gas and hydrogen is a gas, and ammonia is also a gas. So we can see that from our balanced equation, we have 4 molecules of gas reacting and 2 molecules of gas forming. So that's coming from the 1 plus the 3 for the reactant side, which is 4, and then 2 for the product side. So a higher number of molecules means higher pressure. So if we increase the pressure, the equilibrium will be pushed to the right in order to adapt to this, or to relieve the stress. As we've already said in earlier videos, that if you increase the pressure, the side of the reaction that has the least number of molecules will be favoured. So here, if we increase the pressure in our reaction, we know that the product side will be favoured because it only has 2 molecules, where the reactant side has 4. So basically, the higher the pressure, the greater the yield of ammonia. However, we know that high pressure is quite costly, so a compromise pressure of 200 atmospheres is used in most industrial plants. So to summarize here, in this little box here at the bottom, to maximize our yield of ammonia, we need to have high pressure, low temperature, and a high concentration of our reactants. So the contact process is a method by which sulfuric acid is produced, and one of the main steps in the contact process is the reversible reaction between sulfur dioxide and oxygen to produce sulfur trioxide. So the forward reaction is exothermic, so delta H is negative, and the reverse reaction is endothermic, so delta H is positive. And the amount of sulfuric acid produced actually depends on the amount of sulfur trioxide produced. So first let's look at the effect that temperature has. So if we want to maximize the yield of sulfur trioxide, low temperatures are preferable. So to oppose this temperature decrease, the equilibrium will shift to the exothermic side, which is the forward reaction. So if I have a cold temperature, the exothermic reaction is favoured because the exothermic reaction gives out heat. So it can oppose that temperature decrease that has been set up. However, very low temperatures are not used in industry as the rate of reaction is very slow, and that's similar to what we said in the Haber process. So we have a compromised temperature of usually about 450 degrees in our production of sulfuric acid. So let's look at concentration, and we want to maximize the yield of sulfur trioxide because that will in turn maximize the yield of our sulfuric acid. So to maximize the yield of sulfur trioxide, it's the concentrations of the sulfur dioxide or the oxygen that must be increased, because if you have an increased number of reactants or an increased concentration of the reactants, the reaction will want to oppose this increase in concentration, so it'll want to bring their concentration back down, so it will push the reaction forward. Similarly, if we decreased the concentration of the sulfur trioxide, that would mean that there will be less products here. So in order to bring the reaction to equilibrium, more product would need to be produced, as there will have been a drop in the concentration. The last stress we want to look at is pressure, and we can clearly see that we have 3 molecules on the reactant side and we have 2 molecules on the product side, with the 3 coming from 2 plus 1, which is 3, and then 2 on the product side. So that means that if we have a high pressure, it will favour the forward reaction. So the higher the pressure, the greater the yield of sulfur trioxide. However, we know that high pressure is costly, so a compromise of 40 atmospheres is used in most industrial plants. So that's it for today's video. Have a read over the learning intention to make sure you understand everything we've gone through.